Good. All right. Hello, I'm Byron Zhong from the University of Chicago. Thanks for the introduction. And I'm here to present our recent work on closure optimization. This is joint work with Professor Olin Shivers from Northeastern University and my advisor, Reppy, who's in the audience today. Let us start with the subject of study, the closure. So a closure is a code pointer together with an environment, as we all know, which maps variables to values. It is needed to represent a higher order function value in our languages. And the question then we're focusing on today is how we should represent that environment. And the simplest representation, which is also the most widely used representation, is a flat closure. So let us start there. So consider this function. I'm going to use ML-like syntax for this talk that closes over in fact, 5 variables. And together with the code pointer itself, which I'm going to use the superscript C to indicate that K3's closure is represented by the 6th tuple. Now, so K3 is defined in the body of another function K2, which inherits all of these free variables, but except for Y2, which is bound by K2. Now that its closure is represented by this 5 tuple. And now we do this again. If this is wrapped around in another function, K1, this inherits all the other free variables, plus an additional variable C that it only itself uses. And finally, we have the top-level function G that closes over everything, which is not particularly interesting here, so I'm going to omit it from now on. So what does the environment look like under flat closure? It is very simple. The environment is just a tuple of free variables. And despite the simplicity, it has actually 3 really nice properties. First of all, it's really easy to implement, and we don't like to make our life harder than it really is. But second of all, the variable accesses are very cheap. So say if K3 needs to access the variable A, it can do so via one load away from the closure pointer. And depending on who you ask, this is maybe the most important aspect of this. This is proven to be safe for space, which we'll come back to this point in a little bit, but roughly this means that the closure only points to values that it actually needs. But the downside of this approach is perhaps very visible in this diagram already, which is that every new closure repeats part of the environment because they're all free in this. Not only do you have to allocate bigger tuples, but you have to copy values from one closure to another. That is one load and one store for each free variables at each level, which is less ideal. But before I continue with the talk, you may be asking yourself, who cares? Who writes code like this? Right? Fair point. This is extremely hard even for vibe coding tools to generate. But compiler frequently generates these type of patterns, right? One example is, we all know, it's monadic style programming. So say you have this do block here. Each one of these arrow operators, we want to call it, will be desugared into a deeply nested function, which propagates all of its free variables up. A second kind is currying. This should be obvious. That currying defines implicitly a deeply nested functions, which propagates up its free variables. But the reason why we care about this today is because of standard ML of New Jersey. And there's one particular point about SML New Jersey that I want to draw your attention to, which is that it not only uses a CPS-based IR, it also uses a CPS-based runtime system, which means that instead of using a stack to keep track of calls and returns, we use continuation closures to do so. Which means that the closure representation for those continuations has a tremendous impact on the actual runtime. But regardless of how you get to this point, once you're in this point, what can we actually do about this? And we realized that A, B, and K are not actually used in K1 or K2, but instead just there to provide access for K3. So an obvious idea is that we're going to allocate a shared tuple that captures these values, and then we just put a pointer in each one of these closures. So now the closure construction is cheaper because it's one load versus 3, but the variable access becomes more expensive. Now that when K3 needs to access A, it needs to do so via a layer of indirection. And It's also important to note that closure sharing does not describe one unique representation like the flat closure does. Is in fact a family of representations, right? As another example, we can see that y1 and the pointer is shared between k2 and k3. So it's an equally valid choice to put that into a separate tuple. It's not a particularly good choice here, just because it's not big enough, it's not reused frequently enough to actually make a benefit, make an impact. But this highlights the fundamental trade-offs that we're facing. It is that we want to minimize allocations at the same time of minimizing the level of interactions. There's another choice that we can make, which is perhaps a little bit more problematic, which is that we see the C here that is available at the time we construct the closure for K1. If we were to move C inside of that shared tuple, so we did something really nasty here, right? By putting C in the shared tuple, we keep C reachable after it is semantically dead. So what used to be collectible after K1 has been dead, now it is not collectible anymore because K2 and K3 has access to that. This is a space leak, and this is violating this compiler's space safety guarantee, which is not good. At the same time, we have a third choice here, which is that if we somehow find out that K3 is called more often than it's constructed, so for example, if K3 is the last stage of a curried function that we've shown here, which is applied in a loop, we may decide to revert back to flat closure conversion for that ease of access. This will create more allocations, obviously, but the access are cheaper. So this is what we call the closure compaction, which is we choose not to reuse a shareable closure when it is available. So under closure sharing, what does the environment look like at runtime? It is very permissive. The environment is now a DAG with a root, which is a pointer to the closure, from which your free variables are reachable. And we talked about the trade-offs here, and the concerns that we have is that we must balance that trade-off and must not introduce space leaks. So if we widen our imagination just a little bit more and say, why do we have to confine ourselves to using one variable to represent a closure? Why does the graph has to have only one root? Well, it doesn't, right? So that's another idea, an orthogonal idea, if you will, of optimizing closures, which is what we call closure spreading. So instead of using one variable to represent, say, this K closure, which is represented by a tuple, we can just simply use, say, 4 variables to do so. Now that every single one of these 3 variables are variables in the programming language, which will map to registers by the backend. So it's great, because now closure construction is very cheap. It's essentially a no-op. There's nothing to construct, nothing to allocate. Everything is in the registers. Closure access, variable accesses are very cheap as well, because there's nothing to load. Everything's in a register. So what's wrong with this? Number one thing that is problematic, well, not problematic, is maybe a concern of us, is that if now another function f closes over k, instead of just closing over k itself, now it has to close over the spread of k. Now it closes over 4 variables that used to be bound by k. So we basically move allocation from one place to the other, which may not be a smart choice always. And the second one you're probably thinking of right now is that by doing this rewrite, by spreading k across many variables, we change the calling conventions for ID and k. So we have to make that consistent somehow, right? So we need to somehow find out all call sites that could possibly call ID, and I need to find all functions that could possibly flow to k to update the calling conventions consistently. So calling convention must be consistent is sort of the main issue with this approach. But now we widen our permissive environment representation even more. Now the environment is just a graph with any number of roots. So that's our closure representation so far. And it must do so by consistently updating the calling conventions and consider the register pressure downstream. So that is the 2 optimization techniques that we like to do. And it's each with its own trade-offs. And the second half of this talk is going to talk about how we made those choices. And we focus specifically on what information we might need to know. So to make smart sharing decisions, we need to know a bunch of frequency questions. Is the functions defined more often or called more often, which means that should we optimize for closure creation, or should we optimize for a variable access? And for each variable, are they accessed often at all? For spreading optimization, we have sort of a related but different question, which is that what are all variables that could be bound to a function? And conversely, what are all functions that could be bound to a variable? And if you realize that one side of this question, the frequency question, is a question of control flow, and the other side of the question is the question of a data flow. And very fortunately, higher order flow analysis gives us both. It provides a sound over approximation over data flows and control flows. And for this, we designed an efficient, sparse zero CFA analysis in the compiler of CNML of New Jersey, and that works at a scale as well. And by sparse, it really means that unrestricting values such as integers are not tracked at all in this analysis. That gives us efficiency. At the core of this analysis is such a flow rule that says, in module M, U may flow to V. That is what that relation is saying. And this is defined recursively, and the analysis itself just computes the least fixed point of that relation, and then we know that this is sound because it's the fixed point already. So how do we use this? To answer the control flow question, from the control flow analysis, we derive the control flow graph, which tells us actually more than what a traditional intra-procedural control flow graph would do, because it actually tells you for a higher order function f in this filter function here, written in a very standard way, what f really is. If these are all I have in my program code, I know precisely f can either be even or odd. So from this, we can construct an approximate, what we call control flow graph, and then we can do a bunch of ordinary analyses on this, such as loop analysis and branch prediction, and we can answer the question that we're actually interested in. Is f called in a loop? Is f defined in a loop? Is a branch more likely to be taken than the other, etc., etc. And from then, we consume that result by performing a variable usage analysis that tells us how a variable is used, or a free variable specifically, is used in a function. Are they used solely to create other closures? That means that it's a prime target for sharing. Are they used directly on the hot loop path, which means that it's a prime target for compaction? So on the flip side, on the data flow question, we perform what we call the closure class analysis. So this is the same example again, but now that we draw a bipartite graph as follows. We have definitions on one side. We have variable uses of a variable on the other side. We use defs use as standard terminologies for data flow analysis. And we draw an arrow if a function could flow to a variable. Now, each connected component in this bipartite graph is a closure class, and closure calling conventions needs to only be made consistent within the class, but different classes can use different calling conventions. That gives us really granular yet sound control over the amount of spreading that we're allowed to do. So obviously, the next step is that once we know all the classes, we perform a spreading analysis that answers the questions of what the number of variables for each class is that we should spread to, and that is considering the available registers that this class appears everywhere in the program, and also the impact on other closures as we talked about. So once we have both sides of the equation, we can perform our layout decisions. We know a lot more about the program than we originally would without those analyses. So now that we actually make the actual layout decisions by performing a top-down greedy sort of traversal of the program text, and at the end we rewrite the program based on those layout decisions. We're very fond of this design because it separates very cleanly the analyses, which finds about facts of the program, and the decision, which are policies and heuristics, and the actual transformation. And all of these can be swapped out in our development process. Well, the obvious question is, does it work? But before we're talking about that, we need to talk about what is the baseline of comparison. So the baseline the comparison is that the SMR New Jersey actually implements a very sophisticated closure conversion already without using a high order flow analysis. That is the work done by Shao and Appel in the late 90s. And it performs closure sharing already, but they base on an imprecise syntactic control flow graph with a bunch of really fancy heuristics. Because they don't do closure class analysis, their spreading can only be confined to a global decision. In this case, they spread all continuation closures uniformly to use 3 extra variables. And they, obviously, for syntactically known functions, they use the custom calling convention for all of these because they're well known. So we implemented our methods on Standard New Jersey on 2025.2 with an LLVM backend, and we perform a direct comparison by swapping out only the closure conversion part while leaving everything else exactly the same. And we evaluated on both x86 and 64, x86 64 and ARM64 architecture. And we focus on our results here today on ARM64 because it has lots of free registers for us to spread to. And the runtime speedup is significant. And with our method, we achieve about a 10% speedup, the geometric mean across our benchmark suite. In the most extreme cases, we can actually speed up programs by 1.7x. And this drops the runtime from 10 seconds to roughly 5.8, a little bit more than 5.8 seconds. And similarly, we can achieve tremendous allocation savings. In some cases, we're only allocating 16% of the original program, which is, is pretty, in our opinion, is pretty substantial. And lastly, I want to point out some of the other work that relates to ours. First of all, is a defunctionalization question, which focuses on the representation of code part of the closure, while we focus on the environment part of the closure. Second of all is lightweight closure conversion, which focuses on the free variable sets that needs to be closed over. They try to reduce those, while we basically keep everything intact, but only use try to represent those environments in a smart way. And lastly, we have unboxing and error erasing, which closure spreading is sort of an instance of. Right? The main takeaway is that better flow information can be used to make better closure representation decisions, as we've shown here. There's a lot more in the paper, and the artifacts are available. And with that, I'm happy to take questions.
Thank you, great talk. So I was wondering about you have to be consistent with the calling conventions if you start adding variables for your functions. Can't you do eta expansion to kind of fake that? So if you eta expand that, and then you can fix the call sites.
Well, we can, yes. Well, the question is that can we use eta expansion to fix that issue? But then, that makes...
But you introduce a new function, which still has
exactly.
the same issue,
we again move allocation from one place to the other.
But at least if you have a function which is used both in a known and unknown way,
yes,
then you can do the eta expansion to at least consistently optimize the known functions.
Yes, right? That's something that we already do by the compiler. Like, right. If a function escapes and also used internally, there will be a wrapper around it that allows you to customize the internal version, but sort of keep the external version sort of intact.
All right, thank you.
Mm-hmm.
Any other questions?
Thank you. You showed this example of the closer overcapture, which you classified as a leak and inherently bad. But isn't that another dimension for optimization? If there is a price of memory, but there is also you can reuse more of the structure if you overcapture.
Sorry, can you repeat the last part of the question?
Can you use it? Can you consider this another dimension for optimization? If you overcapture the closures, you can reuse more, but at the price of more memory use.
To some extent, we use that here in our compiler. So if we figure that C is actually an integer, say it cannot be a pointer pointing to a giant data structure, we implicitly allow this. And similarly, for this example, K1 subscript C, which is a code pointer, which is not free in anything else, but we consider that sort of not going to be changing the space complexity of our program. So we actually would point that pointer directly to K1's closure instead of being a separate tuple here. So, I mean, that really depends on what kind of guarantees that your compiler is supposed to give the user about the space safety. But yeah, definitely that is something that we do already.
Maybe we can take one more question if there was while the next speaker sets up.
Great talk. Have you considered using profile-guided optimization for this? Because it seems like if you can count how many times a function is created or called, then you can be very precise about how to represent your closure, or which one is better.
Yeah, definitely. In coming up with the decisions, we actually inject a lot of instrumentation code in the generated code itself too. That allows us to validate whether the heuristic, the kind of decisions that we're making are sound or sort of like are making any progress or not. But yeah, definitely, with some setups, we can make it a profile guided way, but that hasn't been done as we consider that as a future work.